stop me if this is not what you also figured out. Okay? First of all, the first thing you guys pointed out to me was that this is 60 degrees and this is 30 degrees, which seemed a little odd, but okay. Right? And then this said, right, read to 2 decimal places the coordinates UV of the point where the ray cuts. So it's right here. And when it says read to 2 decimal places on a graph this size, I have no idea what they really mean. Okay? But of course, we could figure it out, right? Yeah. Because if this is 60 degrees, then this is the side of a right triangle across from 60 degrees. And if this is 1 because it's a unit circle, this has to be 1/2 the square root of 3. Okay? And of course, the distance across this way has to be 1/2. Does that make sense to everybody? Right? It's a special right triangle. This is 1. This is going to have to be half of 1. And this is going to have to be this times the square root of 3. So that's how it turns out. And if you use a calculator, I think you wind up with 0.87 over here. Yeah. And over here you wind up with 0.5. Okay, so I think that's what they're looking for here. Okay, so then it says find cosine of 60 and sine of 60 with your calculator. And if you did, it was probably 1/2 and something like 0.87, right? Yes. And so the question is, how do these things correlate? Well, right, we know, because we've done this before, that the x-coordinate here is going to be the cosine of theta, and the y-coordinate is going to be the sine of theta. Okay? And by calculating it with your calculator, you sort of figure that out, and hopefully see that as a pattern. Okay? Then it says plot the point, 60 degrees, sine 60 degrees, on the theta y coordinate system. This is the theta y coordinate system. So you go out to 60 degrees. Thank you. You go out to 60 degrees, and you come up to 0.87, which would be right about here. Okay? And draw a line segment showing how this point is related to the point you plotted in problem 1. Well, a couple of people drew line segments from here to here and from here to here and said, well, they look like the same angle. And yeah, they do, but that's pretty much because they cheated and made this 30 degrees. But I think what they're talking about is right here, here's a line segment, and here's a line segment. Right? The height on this graph is going to be the same as the height on this graph, because what we're graphing here is the sine, and the sine of theta, under our new definitions, is equal to the vertical coordinate, right? Vertical coordinate v divided by the radius, and on a unit circle the radius is 1. So whatever v is over here, it's also going to be over here on a sine curve. Does that make sense to you? You with me on this? Is this what you figured out too? Is this what your drawing did? Yeah? All right. So then the next thing it says to do is plot. We did that. And it says, without actually calculating any more values, point plots on the graph. Well, if we just figured out that the distance from here to here is going to be the same as the distance from here to here, then what's the sine of 90 degrees? 1, because it's going to be the same height. And 30 degrees is going to be the same height. And this is going to be the same height over here, right? 120 degrees. And 150 degrees is going to be the same height over here. And when we finally get to 180 degrees, it's going to be here. what we're doing here, and this is why I said we're using time as a dimension. Yeah, here we're graphing degrees against sine, but think about the way we were looking at this the other day. If this was the water wheel, right, and this point was going around this circle, well, if we were just looking at it in terms of its position in space, the point on the water wheel would go round and round and round and round, right? If we think about it in terms of its position in time, right, its height, not its back and forth, but its height relative to time, as time goes on, it goes up, it comes down, right? It goes up, right? And that's the graph we're talking about right here. Okay? And I can plot all of those without calculating anything at all because I'm really just using this graph, right? The sine curve is really how high is this dot as it goes around the circle. Okay? So there's two ways to think about it here. One is, of course, by degrees and sine. This is the degree, what's the sine? This is the degree, what's the sine? But the thing that makes this kind of useful in the real world is that as something goes around a circle, or as something repeats itself over and over again, it tends to form this kind of curve. So what happens next? It says connect the points. What geometric figure is this curve? That's what we call it. It's a sinusoid curve because it follows the path of a sine wave. Then over here, in this column, it switches completely. It says instead of plotting sine, plot cosine. Well, okay. What's the cosine of this? Well, we already said the cosine of this was 1/2, right? So, right, 60 degrees, 1/2. That would be about here, right? 30 degrees, how far is this? Well, that's about 0.87, isn't it? Because now this is 30 degrees. Right? This is 1. This is 1/2. Right? And then, right, this is 1/2, and this is 0.87. So this distance right here would be 1/2 square root of 3. Does this make sense to you? Yeah. Right? This triangle right here is the same as this triangle right here. So now watch what happens, okay? Here this is at 30 degrees. Right? This is getting, the distance is to the vertical coordinate is getting, to the vertical axis is getting shorter and shorter and shorter. In fact, what we're graphing here is the horizontal coordinate because the cosine of theta is equal to the horizontal coordinate divided by the radius. So what's going to happen here? Well, this is going to come down, right, and down, and down, and down, where do we, yeah, and down to here, right? And then it's going to go negative, it's going to go over here, so it keeps going down and down and down, and then it's going to come back up. So it looks something, and again, forgive my, right, here we go. Right, goes like this, and then comes down to about here, and then comes back across to about here, and then up again to about here. So if you put in your graphing calculator what's, you know, graph the sine of x degree, of theta degrees, it'll look like this. And if you superimpose the graph of cosine, it'll look like this, only it'll be a much smoother curve. And then they ask you, why do you think the letters U and V are used? Did anybody come up with a reason for that? Here's my thought. Didn't you guys use H for something else last semester? Right? When you were dealing with HK, right? That served a different function, right? So if we used H and V, that would be kind of weird on two levels. First of all, we've already used H for something else. And second of all, XY, YZ, right? We always seem to use letters that are right next to each other. So UV seems like a reasonable thing. I put this sort of in the category of why does M represent slope? Why does M stand for slope? Right. Me either. Right? I don't know either. Maybe. I don't know. But it is what we use. So V makes sense, right? U just sort of falls into place. The real point is, for whatever reason we do it, that is what we do. And that's how these two curves relate to each other.